Hello students, welcome to all. Today we are going to study groups and coding theory. Okay, so we start with groups and coding theory. Coding theory is an important branch of mathematics. Coding theory is an important branch of mathematics that is developed to understand the transmission techniques. Okay, and here it uses the knowledge of group theory as a base. This theory helps in detecting and correcting errors of transmission. So here coding theory is an important branch of mathematics that is to develop to understand the transmission technique, and here it uses the knowledge of group theory as a base. So this theory, this coding theory helps in detecting and correcting the errors of transmission. Now here in this chapter we introduce the basic ideas of coding theory along with some system. Okay, now we start with the coding of binary information and error detection. Okay, coding of binary information and error detection. So see here, when we send messages to our friends, family members, normally we use the mother language or English language. So this language consists of finite number of alphabets to construct meaningful words. Okay, so similarly in binary messages we use the two symbols 0 and 1. So here 0 and 1 are the binary symbols. It is called the set of alphabets. So here 0 and 1 is called the set of alphabet in binary and is denoted by capital B equals to set 0, 1. Set consists of two elements or two alphabets 0 and 1. In fact, the basic unit of information is called a message. So this basic unit of information is called message. Now message in binary digit is defined as definition. A message is a finite sequence of characters from a finite alphabet. So in binary digits, a message is a finite sequence of characters from finite alphabet. So here from the set B that is set contains two elements, two alphabets 0 and 1 of alphabets, we construct the basic unit of information. So this basic unit of information is nothing but the word of length m. So length of that word or length of that basic unit of information is m, that contains m ones and zeros. So see here we see the example 1 0 1 1 0 1. So this information, so information that is this word is given and its length. So see here length that is m ones and zeros. So count number of zeros and ones. So see here 1 2 3 4 5 and 6. So there are 6 ones and zeros. So therefore the length of this word or this information is 6. Okay, since it contains the 6 ones and zeros. Okay, so similarly if we see the second example 1 0 0 1 0 1. Okay, now this is the information, we call this as word of length is the information called a word of length So its length 1, 2, 3, 4, 5 and again 6. So its length is again 6, that is 6 ones and zeros in this word. So all of you get it, how to find the length of given information or given word. Okay. Now next point. The set B, the set B 0, 1 forms a group under the binary operation, addition. So see here, the set B01, observe this set B01, that is here we the set of integers modulo 2, right, that is Z2. So Z2 with respect to the binary operation addition modulo 2 is the group, or this forms a group. So we construct its table. So see here, its table 0, 1, 0, 1 with respect to the binary operation addition. Here set Z2 together with binary operation addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0, 1, but 1 plus 1 in addition modulo 2 we get 0. So from this table we get the set Z2 with respect to the binary operation addition modulo 2 is a group. Okay. Now B square is equals to B cross B. Okay. Similarly, if we take the B cube, B raised to 3, then B cross B cross B. That is 3 copies of B. So in general, B raised to N is nothing but B into B into so on up to B N copies of B. So all of you get it, B square is nothing but 2 copies of B. B cube nothing but the 3 copies of B, and B raised to N is nothing but the N copies of B. Now the set B square, the set B square is a group under the binary operation ring sum. Binary operation ring sum defined as x1 x2 ring sum y1 y2. So here the operation x1 plus x1 plus y1 and x2 plus y2, that is coordinate wise addition. So x1 x2 ring sum y1 y2 is nothing but the x1 plus y1 and x2 plus y2. So the set B square is a group under the binary operation ring sum, and ring sum is defined here. Okay. So if we take the example, suppose we take one pair 1 0 ring sum 1 1. Okay. Now here we apply the operation here ring sum. So we get coordinate wise addition 1 plus 1 and second element 0 plus 1. So that means we get 1 plus 1 is nothing but 2, and in binary, that is in Z2, we get 0. Now 0 plus 1 is 1. Okay, so set B contains only 0 and 1 element, so that's why 1 plus 1 is equals to 2, and with respect to the addition modulo 2, we get 0. Okay, and 0 plus 1 is equals to 1. So 1 0 ring sum 1 1 is nothing but the 0 1. Okay, all of you get it this? So we generalize this result. Generalizing the above fact for b raised to m, we define the binary operation, ring sum as x1, x2, x3, so on up to xn. Ring sum y1, y2, so on up to ym. Okay, so we get coordinate wise addition, that is x1 plus y1, x2 plus y2, so on up to xm plus ym. So here we get x1 plus y1, second element x2 plus y2, so on up to last element xm plus ym. Okay, so this is the generalization for b raised to m, and here we define the binary operation ring sum here. Okay, so b raised to m with binary operation ring sum is a group with identity element denoted by 0 bar. So identity element is denoted by 0 bar, and 0 0 0 so on up to 0 m times. Okay, here x1 x2 x3 up to xm, y1 y2 y3 up to ym. So we take 0 bar 0 0 0 m times, and every element is its own inverse, So every element is inverse of itself. Okay, that is x1 is inverse of itself, x2 is inverse of itself, inverse of y1 is y1 itself. Okay, so the set b raised to m has 2 raised to m elements. B raised to m has 2 raised to m elements. So in particular, if we take the b square, then b square contains 2 raised to 2, that is 4 elements. So in particular, b square has 2 raised to 2, that is 4 elements. Okay, similarly b raised to 3, it has 2 raised to 3, that is 8 elements. and b raised to 4 has 16 elements in general. So a general element of b raised to m is written as a sequence x equals to b1, b2, b3, so on up to bm. Okay, so we call this sequence b1, b2, b3 up to bn a word. So this sequence is called word. All of you get it? This sequence is nothing but the word. Now next, here we see the next point, the transmission of word from one point to another point. So we see the diagram of transmission of word from one point to another point. So diagram, the transmission of a word from one point to another. Okay, so we see the diagram. Word x belongs to b raised to m transmitted. Okay, so here word xt belongs to b raised to m received, and this is the transmission channel. Transmission channel. Okay, so this is the diagram for the transmission of word from one point to another. So word x belongs to b raised to m is transmitted. This is the transmission channel, and we get the received word xt belongs to b raised to m. This is received word. Okay, so here this is the answer for the question how to send or transmit word from one point to another through a transmission channel. Okay, so this is the diagram for the transmission of word from one point to another through transmission channel. Okay, all of you get it, this diagram? So in practice, most of the times this transmission channel suffer disturbances which are generally called noise. Okay, so this disturbances is called noise. The reason may be weather, interference, electric problems, etc. Okay, so this may cause a 0 is received as 1 and vice versa, that is 1 is received as 0. Okay, so as a result, it may happen that a word x is transmitted is different than the word received xt. Okay, so that means x is not equals to xt. So here the transmitted word x is different than the word xt, so that's why this suffers a disturbance. Okay, now in this case, when there is no error, x is equals to xt and both x and xt belongs to b raised to m. If there is no error, that is the word x is transmitted, the word received xt, that is x is equals to xt and these both belongs to b raised to m. So there is no disturbance, no error. If there is error or disturbance, then x is not equals to xt, right? So taking into consideration the real situation, the basic task in the transmission of information is to reduce the error of transmission. Okay, so here the task is to reduce the error of transmission. So for this task, we define an encoding function. For this task, here task to reduce the error of transmission. So to reduce the error of transmission, we define an encoding function denoted by E on the set of words, that is b raised to m. These are the set of words. So E defined as E denotes b raised to m to b raised to n, but n is strictly greater than m. Is a 1-1 function for all b belongs to b raised to m as b to e of b. Okay, so the element e of b belongs to b raised to n is called code word. So this e of b belongs to b raised to n is called the code word. The encoding function is known as order pair mn, encoding function. Okay, so encoding function is known as order pair mn encoding function. So here the definition of encoding function, E from b raised to m to b raised to n greater than m is a 1-1 function for all b belongs to b raised to m as b tends to e of b, and this e of b belongs to b raised to n and this e of b is called the code word. Okay, so all of you get it, coding function. Now the encoding function must be 1-1. Encoding function must be 1-1 function so that different words in b raised to m will be assigned to different code words. Okay, so encoding function must be 1-1 function. So here we see the figure of encoding function. So first word b belongs to b raised to m to be sent. So encoding function E, encoded word x equals to e of b and this e of b belongs to b raised to n. Okay, so this e of b is called code word. After it is transmitted through transmission channel, we get received word xt belongs to b raised to n. Okay, so this is the figure of encoding function. All of you get it this? Okay, so today we stop here. Thank you.